Okay, so thanks a lot for the introduction, and thanks a lot for inviting me and giving me the opportunity to talk to you now in the next 30 minutes about crystalline silicon solar cells. So I will give you a little bit an overview of the state of the art of the technology and some of the future challenges. And I will start first with a general introduction about photovoltaics. So starting here from this well-known curve, the so-called learning curve of photovoltaics. So this actually shows the cost, or let's say the price of a PV panel from 1976 until end of last year. And you see there has been a continuous reduction in the price of the PV panels. In fact, in 1976, the panels were very expensive, $100 per watt peak. But because of mass production and lots of technical evolution, of course, in the last 50 years, we see now today it's only 8 cents per watt peak. So basically, we can say that it's almost 100% reduction in the cost in the last 45 years. And to bring that in perspective, if you just consider if you would want to have 3 kilowatt system on your roof, for instance, just for the modules alone in 1976, you would have paid $300,000, which is basically the cost of a house. Whereas today you would pay only a couple of $100. So it's a huge difference. And some other numbers of the last years. You see here the amount of PV modules produced. So in 2023, it was around 500 gigawatt peak. In 2024, it was already 700 gigawatt peak. But basically, there is an overproduction. So there are more PV panels produced than are actually sold. And that also explains the very low cost here and the huge drop in the last years of the price, basically. And in principle, although we only installed around 500 to 600 gigawatt peak of modules in 2024, in principle, the production capacity was already capable of producing 3 times as much. So there is a lot of production capacity at present. And if we look to these numbers and we look to the technology behind it, we can say that most of the PV panels, 98% of the panels that are being sold, are actually based on crystalline silicon. You have, of course, alternative materials, so-called thin film materials, for instance, cadmium telluride or CIGS, but they have only 2% market share. So if we then look to the evolution over time of how many PV panels have been installed worldwide, so here you see for each year the cumulative amount of PV panels that were installed. We see that in 2022, we surpassed the 1 terawatt level. So 1 terawatt means 1,000 gigawatts, so 1 million megawatt of PV was active. So it took, let's say, from 1976 until 2021 to install the first terawatt. But it took only 2 years more to go from 1 terawatt to 2 terawatt. So you can really see that there is an almost exponential increase in the installed capacity. So in this talk, I will focus on crystalline silicon photovoltaics, and you can roughly distinguish in the value chain going from sand to a PV panel based on crystalline silicon. You can roughly distinguish 5 different steps. First, we have to make very pure polysilicon, starting from quartz or sand. Then this polysilicon is molten and a very large ingot is produced. The ingot is then wire sawn into individual wafers. The individual wafers are processed into individual solar cells. And then the solar cells are interconnected and encapsulated in the PV module. Traditionally, there were 2 types of crystalline silicon being used, multicrystalline and monocrystalline, but as I will show you later, today the market is 100% based on monocrystalline silicon because monocrystalline silicon wafers have less defects, so you can reach much higher cell efficiencies with them. Here, we, if you zoom into this small part of the graph, you see actually the distribution of the cost. So we know the cost of the PV module based on silicon is only 8 cents per watt peak at the moment. How is this cost distributed over the value chain? Well, actually around 40% of the PV module cost is really directly linked to the silicon wafers. So the wafers are really a very expensive part, but of course also crucial part of the technology. Then you have another 40% of the cost that comes from the materials that we use at module level, and also partially the module assembly, the processing itself. And only less than 20% is actually directly linked to the cell cost. So this is something to keep in mind. We have silicon wafers as the heart of the technology of silicon photovoltaics, but they're also responsible for 40% of the cost. So if we want to reduce the cost, we also have to look to the wafers. And then finally, we're talking here a lot about the PV module cost. If you're going to use PV modules, you of course need to have more than just the modules. You need inverters, you need to make the whole system. So everything else that you need for a PV system that is not the PV modules are called balance of system. And actually the balance of system cost is typically 70% of the total system cost. So the modules today, they are responsible for only 30% of the cost. And this is also very important to understand because it really pushes PV modules not only to low cost, but also to high efficiencies. If you have a high efficient PV module, you need less area because you can produce more power with less area. And this will actually be very beneficial at balance of system level. So this is why actually it's not sufficient to have a low-cost PV module. The PV module also needs to be really highly efficient. So in the next 20 minutes, I will say a few words about how the silicon wafers are being made and why they are so expensive. Then we will zoom in into the solar cell processing. I will say also a few words about module processing and the state of the art there. And then finally, we will look to some of the remaining challenges for the technology, especially if we want to become climate neutral as a world by 2050, it's quite challenging. So first we'll have a look to crystalline silicon wafer formation. So we saw already the silicon wafers are responsible for 40% of the cost. And if we look to the energy demand, so the amount of energy that you need to produce a PV module, then it's actually even more. It's around 60 to 65% of the total energy to make the PV module is really needed to make actually the silicon wafer. And so the reason that we need so much energy and that it's so costly to make the wafers is actually shown here. This shows you the steps that you need to undergo to come from sand, high purity sand or quartz to the silicon wafer. And for each step, it's also estimated how much energy you need per kilogram or per square meter to produce that step. And so we have a lot of high energy intensive steps, a lot of high temperature steps are needed. So first, you need to go to very high temperatures in the furnace to make the sand into metallurgical grade silicon. The metallurgical grade silicon is already relatively pure silicon, but not pure enough. So we have to further purify it. So this is basically done in the gas phase by a kind of distillation. Then we have a very pure silicon gas. We have to go back to the solid state. So for this, we again need a high temperature reactor, very high temperature. So lots of energy needed to create a polysilicon. But then the polysilicon has to be remolten and reshaped into the ingot form. So again, you need to go to very high temperatures, so above 1400 degrees, the melting point of silicon to form the ingot. And then finally, we are wire sawing the ingot into individual silicon wafers, but we're also losing a little bit of silicon there because of the cutting process. So in total, we have a lot of high temperature steps, a lot of energy that is needed. And we estimate that you need around 0.35 kilowatt hours per watt peak that your wafer will produce. So it's quite a lot of energy, and that explains why it's also quite expensive in the end to make these wafers, and they are responsible for 40% of the total module cost. So if we now look to some trends of the recent years, so today in the industry, everybody is using these very large wafers that are called M10 or G12 that are typically 180 by 180 millimeters or 210 by 210 millimeters. If we go back a couple of years in the history, then for a long time we had a standard size which was much smaller. It was only 156 by 156 millimeter. But today we can make much larger wafers in a very good controlled way. The wafers are very stable, although they are also quite thin. They're only 150 micrometer thin typically. And this actually at the cost gives a cost benefit. So everybody is using these large wafers. And so you see here in this graph from the ITR PV roadmap, you see the market share of the different wafers. So at the moment in 2024, 2025, everybody is basically in industry using these very large wafers. And here we see a little bit the evolution over time, over the last decade, of what type of silicon wafers have been used. So you can see if we go to 2016, 60% of the market was based on multicrystalline silicon. So this is a slightly cheaper silicon wafer, but it has grain boundaries. It has many defects inside, so you cannot really go to very high efficiencies with this type of wafer. And as I explained, we really need highly efficient PV modules. And so we've seen actually, because of this push towards high efficiency, that today actually there are no multicrystalline silicon wafers used anymore. So everything is monocrystalline silicon since a couple of years. And we also see a second change. So in the past, until a couple of years ago, most of the wafers that we were using were P-type, so they were doped by boron. Today, actually, we use mostly N-type silicon wafers. So the N-type is dominating. Again, for the same reason, it is slightly easier to go to really high efficiencies with N-type silicon wafers compared to P-type wafers. And that's why we are switching in the industry from P-type to N-type. So everything is always driven by cost and high efficiency. So now we have talked a little bit about the wafers. How do the wafers now get processed into devices, into silicon solar cells, and what devices are being processed? So here I show you again a figure from the ITR PV roadmap of this year that appeared a couple of weeks ago. So here you see for 2024, the market share of different technologies. And I don't have the time to go into the details of these technologies, but for the last 5 or 10 years, the so-called PERC, passivated emitter and rear contact structure, was basically the dominating technology that was being mass produced. But now, in 1 or 2 years' time, actually, the domination of this technology has completely been removed. And now, actually, so-called passivated contact solar cells like TOPCon and silicon heterojunction are being produced in the biggest quantities. And I will explain these device types in the next slides. The same reason, why did we switch in the industry from PERC to TOPCon now? That is simply because with TOPCon, you can go to higher efficiencies. With PERC in industry, we could reach, or let's say in the lab, you can reach 24%. With TOPCon, as I will show you, you can reach close to 27%. So much higher efficiency. So it will lead to lower cost at system level. So the TOPCon cells, as I mentioned in the previous slide, are now dominating the market. And you see here the cell structure of such a device. And TOPCon stands for tunnel oxide passivated contact. And basically, why you can go to higher efficiencies with TOPCon compared to PERC is that we are doing something to the weak point of the PERC device, that is the rear surface passivation of the wafer. So in a TOPCon solar cell, you have at the rear of the silicon wafer, you have a very thin tunnel oxide. And on top of that, a doped, typically polysilicon thin film. And that's why the name arises from this. It's a tunnel oxide passivated contact. You have a tunnel oxide and then a doped layer on top. And this gives you carrier selective contacts. So now at the rear, we will, for instance, attract the electrons to come to that place, but we will reject the holes. So we get a very good surface passivation at the rear. And this actually leads then to the potential of reaching very high conversion efficiencies. And so late last year, the record for this type of device in terms of cell efficiency was set by a Chinese company, Trina. and it's around 27.1%. So it's really very high efficiency and much higher what you can reach with PERC cells. A second type of passivated carrier selective solar cell that is being mass produced more and more is a so-called heterojunction cell. So this is a quite different way of making the silicon solar cell. It's called heterojunction because now we use the crystalline silicon wafer, but we put amorphous silicon layers on top of the surfaces to passivate. So again, this leads to very good surface passivation at both rear and back. You get carrier selective contact. So on both sides now, you are only attracting one type of charge carrier, and you are pushing away the other one for extra surface passivation. And here also the maximum efficiencies achieved so far are close to 27%. So it's very similar in terms of efficiency, although the device is quite different in terms of production, but the resulting efficiency is quite similar to what we can reach with TOPCon. So these are the two, the TOPCon and the heterojunction are the two cell types that at the moment in 2025 are dominating the market. But there is already a next generation being prepared. These are so-called back contact cells. So in the previous cell structures, we still have always a contact at the front and the rear of the device. So on both sides, you have one contact, one polarity. This is the traditional way. But we can also put all the contacts on the back side. That's why it's called a back contact cell. And that has as the advantage that you don't have shadow losses at the front, and you can typically still go slightly higher in efficiency. And actually, quite recently, a couple of weeks ago, a new world record silicon solar cell efficiency has been achieved with this type of structure. And the efficiency, the new world record, is now 27.8%. So that is the highest efficiency that has ever been reached by a single junction silicon solar cell. The previous record was something like 27.4. So this is very high efficiency because theoretically, the maximum efficiency that we can get with single junction silicon solar cell is 29.4. So this is the best we can ever do. And with 27.8, we are getting quite close to that. So in the past, colleagues from Fraunhofer ISE made this roadmap for different device structures and the efficiencies that we can reach in mass production. And mass production efficiencies will always be a bit lower than, of course, the best you can do in the lab. And so they foresee that at this time, which is correct, we are producing the passivating contact devices, where probably we can reach at module level, or let's say at mass-produced cell levels, efficiencies around 25 or slightly higher. Then we will at some point switch in the industry to the passivating contacts with the back contact solar cells, where we can probably reach around 26%. But then it's basically sort of stopped. If we want to even further increase the efficiencies just for a single junction device, it will become more and more difficult because we have to fight against intrinsic things like Auger recombination, which cannot easily be resolved. So the solution for that to go even further in efficiency will be to go to tandem devices, to go to a multi-junction device. And I will quickly explain the idea behind that. So if we look to the single junction silicon solar cell, with which we can now reach 27.8% as a record efficiency value, we see that we lose a lot of the energy of the incoming light, especially because of thermalization losses. So all this gray part here is energy that is lost from photons that do get absorbed, I mean, by the silicon solar cell, but where, because of thermalization losses, we actually lose this energy. So we only use part of the energy of the incoming photon. But if we go to a tandem device, which means we take the silicon as a bottom cell and we put a high bandgap material on top, so a second solar cell on top, then we can actually make better use of the spectrum of the incoming light. And part of the photons, the high energy photons, the blue part here, will be absorbed and converted by the top cell. And you see that because the band gap is higher, we can use more of the incoming energy of those photons. We have less gray area here, less losses. And then everything, all the light that is not absorbed by the top cell will be absorbed in the bottom cell. And there, of course, we have the same thing as before, because it's a silicon bottom cell. But theoretically, this means, whereas with a single junction silicon solar cell, you can reach only 29.4%. Here we see that by going to a tandem device with a bottom cell of silicon, which has a 1.1 EV band gap, in principle, it is theoretically possible to reach efficiencies up to 40 to 44%, so much higher. And of course, you need to have a good top cell. And the top cell requirements are typically you need to have a high band gap, which to match with silicon should be around 1.6 to 1.7 EV. The top cell needs to be highly efficient and stable, etc., of course. And you should have minimal sub-band gap absorption. So it should allow the light that cannot be absorbed by the top cell to pass through and go to the bottom cell. And at the moment, the perovskite material, and I think already yesterday there was a talk about perovskite, so I will not go into detail there. I don't have the time, but the perovskite material at the moment is regarded as one of the most likely candidates. So this means if we go back to this roadmap, that once we go beyond the back contact solar cells, if we want to further increase the efficiency and probably even push it beyond 30%, we have to go to tandems. And just to show you some recent tandem results, the world record solar cell for perovskite on silicon, that record was also recently broken, is now at 34.8%, also by the same company, Longi, that has the world record for the single junction. So for a single junction, we have reached 27.8%. And for if we put a perovskite on top, we actually increase by 7% absolute to 34. So it's really worthwhile to go to these tandems. We really clearly see the potential of having very high efficiencies. This world record is still on a small area, but even for large areas on large wafers, efficiencies above 30% have already been demonstrated. So, okay, now we have seen a little bit about the solar cells. Of course, the individual solar cells, they will be processed individually, but they then at some point have to be interconnected and they have to be laminated into a PV module. So there are different processes being used there. I don't have the time to go into detail, but just like the wafers have increased enormously in size the last years, also the resulting PV panels have been increasing in size. So 10 years ago, a standard silicon PV panel was like 1 meter by 1.7 meter, had 60 small cells. Today you see different sizes, and the largest ones are typically 1.3 meter by 2.4 meter. So much larger, and of course having also much larger power output. So because of these large size modules, we actually today see in the market, so these are really an overview of PV modules that can be bought. So because of the large size and the high efficiency, you see actually modules appearing that have more than 700 watt peak for a single module. Whereas a couple of years ago, typically, we only had around 400 watt for a very good PV module. And here you see some of the efficiencies at module level, the best in class in 2025. So you see for the PERC, which we produced in the past, it is around 22%. But for TOPCon and silicon heterojunction, we are way above that with more than 23%. And we're getting close with the back contacts to 24%. And that's why PERC is being produced less and less, because the efficiency is much smaller. And here you see the projected efficiencies by 2035. So there is still some room for improvement for the TOPCon heterojunction and IBC to values, let's say, somewhere between 25 and 26. But then if we really want to make a big step forward, we will have to go to tandem devices. Tandem devices at the moment, they still need a lot of R&D. They are not really upscalable enough yet, not stable enough yet. but this is really the way forward for the future. And then just as a note, because it's worthwhile to understand that, I think. So we are producing the solar cells on very large wafers. So you have one solar cell produces, because of that, a very large current, because it's a very large area. So the currents can typically be 17, 18 amperes. So this is a lot of current to transport from one cell to the other if you put it into a PV module. And so actually to reduce resistive losses, typically before the cells are interconnected and put into the module, they are typically cut in two. So you see here, most PV modules that are made, they are based on half cells. And some are even based on cells where it's only 1/3 of the size. The main reason for doing that is if you reduce the area of the wave of the cell by 2, you also reduce the current that it produces by 2, and you have much less resistive losses. And this gives you a little bit extra power. And then finally, we can look a little bit to the future. And so we have now worldwide around 2 terawatt of PV installed and active. But we know if we want to become climate neutral, if we want to have net zero greenhouse gas emissions by 2050, then we need much more renewable energy operational, so wind energy, but also PV systems. So we need probably between 60 to 80, so let's say 70 terawatt peak. So in the next 25 years, this means we have to go from 2 terawatt installed to 70. So we need to have another factor of 30 or 40 times the amount of PV installed as we have today. So this is quite challenging, poses a lot of challenges, especially with material use. So also recycling of PV panels will be very important in the future. And I always illustrate this challenging material use with this paper from a few years ago. So in this paper, they looked to PERC production. In 2021, there was around 180 gigawatt of PERC produced. And then you can list all the materials, or let's say not all the materials, but some of the materials that you need at system level to make this 180 gigawatts to produce it and to install it. And you see that you need very large quantities of all kinds of materials. And especially, you need a lot of silver. So each PV module contains a little bit of silver that is used for metal contacts of the cells. It's only a few grams per module, so it's not a lot, but because we make so many modules, it becomes quite a lot. So at that time, we used already 8% of the yearly production of silver just for PV. So most people don't realize that. Now, if we have to scale up, because in the next years, we will have to produce on a yearly basis something between 1 to 3 terawatts of PV modules per year. So if we want to do that, for instance, 1 terawatt of PERC production, and the previous slide we had 180, so you basically have to multiply all the numbers by 5, and you would see that for silver, you would need 43% of the worldwide production. So that's a lot, and that's not realistic. So what they have done in this paper, they have assumed that for any material that we need, a single technology like PV can probably never get their hands on more than 20% of the yearly production. So if we assume that the max amount of silver we can use is 20% of the yearly production, then we can calculate how much silver we can actually allow per gigawatt of production. If we either want to have 1 terawatt production per year, then it would be 6 tons per gigawatt. Or if we want to have 3 terawatt per year, then you have to divide this number by 3. And then we see that for the different technologies, the actual amount of silver that we are using today is substantially higher, which shows that the technology is not ready yet for the massive deployment that we need in the coming decades. I did my own calculation. So in 2023, if you look to there was around 500 gigawatt of PERC and TOPCon produced. This amounted to around 18% already of the annual silver production that we used at that time. So this was only 500 gigawatts. So if we have to go to 6 times more, 3 terawatt, then we almost need all the silver that is produced. Moreover, there are other reasons why we need to use less silver, because silver is of course also expensive, and it accounts for around 1 cent per watt of the PV module. So this becomes very substantial, because at the moment the cost is only 8 to 10 cents per watt in total. And we have actually the same problem with some other materials like indium that is used in TCOs, for instance, for the Tandem devices, bismuth, which is used in smart wire technology. So the main takeaway message here is, although sometimes people think crystalline silicon PV is a mature technology because it's so successful and it's now produced in huge quantities, it still is not fully mature in the sense that for the scale of the deployment that we need in the coming 2 to 3 decades, the technology is not suitable yet. So we have to further develop it. It's not fully developed yet from that point of view. So with that, I come to my summary. So silicon PV is dominating the market, and actually it took quite a lot of time. We started in the 70s already with this technology before it really became this big successful commercial product with low enough costs. So it always takes quite some time. The silicon wafers are responsible for the largest part of the cost and the energy of the silicon PV module. With the solar cells, we are getting closer and closer to the theoretical limit of what you can do with a single junction. And because of this, the whole industry is now, and the whole sector is now actually looking to develop silicon-based tandems that will allow us in the coming decades to go beyond 30% efficiencies in mass production. And by 2050, we have to increase the installed PV capacity from, let's say, 2 terawatt to 70 terawatt roughly. And this will still require a lot of further fine-tuning of the silicon PV technology. So with this, I would like to thank you for your attention, and also like to acknowledge a lot of my co-workers, both at IMEC and at TU Delft, who have contributed to this presentation. Thank you.